a minute ago. You said, electronics last forever because there's no moving parts. What if I blew your mind and told you that there were moving parts? You just can't see them. There's certain failure mechanisms where, the current flows in one direction. The negative charges go that way, and the atoms get enough energy through, usually thermal, to actually start moving in the other direction. Thermal energy is, a lot of times people confuse temperature and heat. Heat is the movement of thermal energy. Temperature is the measure of it, right? We kind of measure the average kinetic energy. And as you put energy into atoms, these things don't just stay stationary. They jiggle around in all sorts of different directions, and they move around in all sorts of different directions. And kind of like, the Newton's cradle toy, it's 5 silver ball bearings. You drop one at one end, and all of a sudden the one at the other far end flies out, right? Well, the same thing's happening with these atoms. If you give them enough energy, enough vibration, enough other atoms, hit at just the right time, at just the right spot, it can shoot an atom out the other side. And, that's the movement that can eventually lead to failure.
That's my guest, Mark Hughes, and his colleague Greg Ziraldo, next on Reliability Matters.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
My guests today are Mark Hughes and Greg Ziraldo. Both work for a Colorado-based contract manufacturer, Advanced Assembly. Mark Hughes spent 15 years as a physics teacher for high school, college, and to other physics instructors. Mark transitioned from academia into the role of staff technical editor for AllAboutCircuits.com, a website that targets electrical engineers with educational content. Mark spent 15 years as a physics teacher for high school, college, and to other physics instructors. Mark transitioned from academia into the role of staff technical editor at AllAboutCircuits.com, a website that targets electrical engineers with educational content. Mark is now the research director with Advanced Assembly, where he splits his time between research and creating educational content for inclusion in white papers, industry articles, and technical videos. Greg Ziraldo is the Senior Director of Operations at Advanced Assembly and has 15 years of experience in prototype, aerospace, and defense electronics manufacturing. Welcome to the show, Mark and Greg. Thanks so much for joining me today.
Thanks so much for having us.
Hey, I sent you a list of, talking points that I'd hope to talk over, but I'm going to throw you a little bit of a curveball just because this is in the news and I'd like to get your kind of fresh perspective on it. Let's talk about coronavirus for a second. IPC has just announced that they expect there to be component disruptions and other supply chain disruptions with regard to coronavirus, particularly given the fact that most of everything we build comes out of China. They're experiencing it more than any other country at the moment. Has that landed on your fabrication business or your assembly business at all yet? Have you seen any signs of what IPC is predicting?
Absolutely. So we have already seen a few letters sent out, emails sent out as alerts to disruption in just supply chain as far as stuff that's coming from overseas, not being able to guarantee delivery, not being able to guarantee really anything at this point, depending on the source of where it's coming from. So we have not seen it actually physically impact us yet, but there has been warning and notification coming out from our top tier vendors saying that this is a real possibility. So when it comes through, we told you so.
Yeah. Okay. They're all CYAing themselves a little bit now.
Pretty
right?
much. Yes. Yeah. Yes.
Yeah. It's kind of a scary thing. I'm not sure at this point, by the time people hear this, maybe this comment will sound silly, but I'm not sure if it's an overreaction or an underreaction or a cautious reaction. It's a little too early to tell, but certainly it is affecting the world. I went out to Home Depot yesterday to buy a mask, a respirator type mask, because I had a sanding project that I was going to do. I was going to sand off some drywall and do a little work on it. And nope, can't. You can't get them, and they have no idea when they're going to be in stock. And I went to the painting department, the wood
the exact
department.
same thing happened last weekend too.
Yeah, everyone
Same
is.
thing in Colorado. Yep.
Yeah, I even went on Grainger. I had my company buyer, go to Grainger. The public doesn't generally buy from Grainger. I'm sure they're not affected. Nope, they're out of stock on any kind of face respirator until they're saying May, which probably means 2,000 years from
May,
now.
holy cow.
Well, and I think May is just a guess. I think if it said 8 days from now, I would think that's probably accurate. The fact that they went May and this is February, I think they just don't have a clue. So they're just putting some date out there. So it's
an arbitrary date out in space at this point.
I think so. They have to put something in, right? So they're putting May. Wow. So anyway, so that just the fact that there's a shortage creates a panic, right? Which makes an even greater shortage. But anyway, it's interesting to hear your take on that you're starting to get all the warnings as well. We're seeing the same thing in our part of the world.
Yeah, I'm really hoping it doesn't disrupt our supply chain or anything like that. Obviously, with what we're doing from a turnkey level from kit assembly, it would be detrimental to what we're doing, but keep my fingers crossed.
Yeah, for sure.
It's also helped us out with sales significantly. We've had many of our offshore customers who had to turn back onshore. We're still creating boards. We're still fabricating, assembling, making things happen. Where over in China, maybe some of their employees haven't even come back to work yet because they can't.
Right. So advanced assembly is, I think, a little bit unique in that you're both a board fabricator and a board assembler. That's not always the case, particularly, most CMs will provide a service for their customers to go buy boards from a board shop. But you guys actually are fabricators as well as assemblers. Is that correct?
We are under common ownership for fabricators. So we don't actually fabricate here directly in Aurora, Colorado. All of our assembly functions are done out of Aurora. The PCB fabrication is done in Hollister, California, as well as Santa Fe Springs, just outside of LA in Southern California.
So let me just make sure I heard that right. You are fabricating boards in the United States of America.
Correct.
Yeah.
Some people may consider California not part of the United States of America, or wish it wasn't. I live in California, so I always take great offense to that. But I understand people's point of view. But that is unusual, particularly in California, because California has extremely stringent environmental regulations. Basically we say in California, if the product works well or it's fattening, it's either illegal or tastes good, one of the two. So
it's funny. What is totally ironic about that is actually California is tenfold more lax about the EPA regulations for PCB fab than Colorado ever is. Colorado is so down to the minutia on the fab side as far as wastewater, waste product, and that's why a whole lot of PCB shops don't exist in Colorado anymore. But you go out to California plants, and it's a whole other ball of wax.
Hollister, I can understand being a little bit more lax because that is not, a big major urban center. But you said Santa Fe Springs?
Yeah,
that's the LA area. That is in the heart of the urban part of Southern California. So I'm surprised at that.
Well, we just brought that factory online. What was it, last year, Greg? It's pretty new. It's got its own water purification systems in-house on site. They did a lot of engineering just to make sure that we wouldn't run afoul of regulations now or potentially in the future.
Oh, very good. That it's nice to hear. So for all of you who are running businesses outside of California, come on. It's safe. It's safe to get back in the water. So when I was a kid, I had this thought in my head that electronic products lasted forever because there's no moving parts, unlike a electromechanical item. And obviously through my experience as an adult and education, I realized that's not true. I've seen the error of my ways. So I read an article that y'all wrote, and you state in that article, I think Mark, you wrote this article if I'm correct, that all products fail given enough time. So my question is, what are some of the methods that you recommend to determine a product's life, particularly when you're trying to figure out what the warranty of the product should be or what the support costs would be over the next many years? What are some test methods that you're aware of that maybe you utilize or your company utilizes to determine kind of a crystal ball to predict the life of a product?
Well, that, sir, is a complicated question, and
we have 4 hours. We have 4 hours, so take the time.
I guarantee you that I'm going to wander off topic at least once every 5 minutes for the next 3 hours and 55 minutes.
I'm hoping you will. I'm hoping you will. Yes.
But you said something a minute ago. You said, electronics last forever because there's no moving parts. What if I blew your mind and told you that there were moving parts?
Are we talking about electrons and semiconductor switches and things like that? Gates?
Well, we're talking about that, and we're actually also talking about atoms physically moving.
Oh, you're getting technical on me now.
I know. So, there's certain failure mechanisms where, the current flows in one direction. The negative charges go that way, and the atoms get enough energy through, usually thermal, to actually start moving in the other direction.
Mm.
And that's actually, as I recall, one of the very, very first failure models that was developed. Oh gosh, I want to say the gentleman's last name was Black, and he worked at like Motorola, and he modified something called the Arrhenius equation that was used in chemistry. I don't know if you remember back to chemistry, but do you kind of vaguely remember that hot reactions happen faster than cold reactions?
Right.
Okay. Some examples of that you might have seen in life is epoxy. If you ever mix up some epoxy and it's a little too cold, it just never will turn. It'll never set up.
Right.
But you do it on a nice, hot, sunny day, and your 5-minute epoxy, maybe it has 2 minutes of work time.
Right.
So thermal energy is, a lot of times people confuse temperature and heat. Heat is the movement of thermal energy. Temperature is the measure of it, right? We kind of measure the average kinetic energy. And as you put energy into atoms, these things don't just stay stationary. They jiggle around in all sorts of different directions, and they move around in all sorts of different directions. And kind of like, the Newton's cradle toy, it's 5 silver ball bearings. You drop one at one end, and all of a sudden the one at the other far end flies out.
Mm-hmm.
Right? Well, the same thing's happening with these atoms. If you give them enough energy, enough vibration, enough other atoms, hit at just the right time, at just the right spot, it can shoot an atom out the other side. And, that's the movement that can eventually lead to failure. But that's not the only thing that's moving. Electrons. These things are flying all the way around, doing all sorts of stuff. And as electronics engineers, we typically are comfortable with 2 states, on and off, plus or minus, true or false, right?
Sure.
We don't often think that these electrons can do this thing called tunneling, right? They can jump through dielectric materials. They can start forming conducting paths through insulators, and they can do that over time. So one failure mode, we've got temperature can accelerate all of this. We've also got this thing called time-dependent dielectric breakdown. You just let these electrons move around long enough.
And we're not talking about electrochemical migration here. We're not talking about ionic residues left behind. This is something deeper than that?
I talked about both. So the first thing I kind of mentioned was electrochemical migration. That's the atomic movement. I just didn't call it that. But no, we're also talking about electron tunneling, which is a physics phenomenon. That the electrons can start jumping through conductors and just magically appear from one side of the conductor to the other.
Like a termite problem in wood. I mean, it literally burrows through the dielectric material, not on the surface, but within the material itself.
Yeah.
Wow.
So that's a failure mode called time-dependent dielectric breakdown. And then there's hot carrier injection, negative bias temperature instability. There's lots of different models for different types of failure. And I want to say of the ones I've mentioned, you could probably trace 3 back to the Arrhenius equation. If you ever want to go look at it. So how do you predict it? Well, you can do it with those equations, you can look at each of your, okay, so coming off of the die inside a computer chip, we go from the die, we go to the bonding wires. We go from the bonding wires to the lead frame. We go from the lead frame to the solder. We go from the solder to the copper traces. We go from the traces to the vias. Right, you start tracking all of those paths, and every connection has a potential failure mechanism associated with it, sometimes several of them. So you can go through and you can calculate them if you want. I personally wouldn't, but it can be done by people with more ambition than me.
And not much to do otherwise. Yes.
Or you can get yourself a software package. ANSYS has Sherlock. I think they have a trial you can play with.
That's right. That came from originally DFR Solutions. Yeah.
So, but you upload your board files and you let it, do its thing. BQR is another company. They've got an online MTBF, so I'm sorry, mean time between failure, that you can actually get from DigiKey's website. So if you just kind of want to play around and see what temperature does to stuff without looking at all of the icky math, if you go to DigiKey's website, they've got a little thing on there called Tools, and I want to say after that you click on EDA and Design Tools, and then you'll get to BQR. It's just a spreadsheet. You put in your components, and it's got the failure statistics on there that you play with.
Wow.
Okay.
Interesting.
I'm not done, man. I'm just going to
keep going. Keep going.
You can delete me later.
Ride that train.
So how do you do? So, how do you do all this? So, essentially, you look at what the predicted failure mechanism is. Let's say that it's going to be temperature, because the higher the temperature, the more energy that you're putting into these systems, the quicker they're going to fail. Temperature is the average kinetic energy, right? It exists on a spectrum. It's not really a Bell diagram, but it kind of looks like one that's skewed a little bit over to the side. So if you've got something at one temperature, you've got atoms that are moving really, really slow over on the left. You've got on the far right-hand tail atoms that are moving really, really, really fast. Those are the ones that are going to start moving around and causing you trouble. Higher the temperature, the more of those you have, the faster it's going to fail. So manufacturers do these things called accelerated testing,
right,
where you will take let's say we're looking at a diode, and an LED diode, and you take it and you put it in a test chamber at 90 degrees Celsius, and you just run it until it dies and say, okay, I did that. And then you go and you grab 10,000 more of those and you do the same thing. And you start getting failure statistics at 90 degrees Celsius. Well, they use this modified Arrhenius equation, in one of those other forms, to backtrack and say, okay, well, now I can predict what's going to happen at 40 degrees Celsius, right? If it lasts 100 hours at 90, maybe it's going to last 50,000 hours at 40 degrees Celsius type thing. So you do this accelerated testing. And if it's conceivable, you would actually back that up with physical testing. You would go grab 100,000 components, throw them out in some warehouse in, I don't know, let's say Africa. I don't know where the manufacturing warehouse is. And you just let them sit there and you just run them until they die. And you actually can start correlating the accelerated testing with the, with actual real world conditions.
So you can kind of predict the curve.
Yeah.
You can connect those dots between extreme and maybe average or average extreme.
Yeah, but not everybody does it right. So one of my favorite examples is, are we allowed to say company names? Do you know?
Of course. Well, I don't know.
Okay,
but, from my perspective, I don't know about yours, but sure.
Okay, so I'm just going to say it rhymes with schmanalog.
Schmanalog Levices.
Yeah.
Yes, I got it.
We'll let your your podcast listeners come in with that. But
yeah, I'll get a bunch of notes in. Yes. Yeah. A prize. Here's a prize, a copy of my book to the first person who answers who solves the puzzle correctly.
Okay, so they've got this number on their website, and I actually, just because I love this example, I looked it up this morning, so I have it here on a Post-it for you. All right, So you go to Schmanalog Levice's website and you go to their reliability statistics page. And for their silicone dies, they've got a mean time to failure at 55 degrees Celsius. They've calculated this to be 68,342,781,460 hours.
Well, I'd give that a good warranty.
I mean, you would want to think so. But they came up with 7.8 million years. And they didn't just come up with 7.8 million years. They came up with 7.8 million years down to the nearest hour.
Right. So clearly that's an educated guess, because they have not run that many hours of testing or years of testing. Obviously, they'd have to start before the Earth was built.
Humans didn't exist. I don't
That's
even
right.
know if great apes had evolved at that point.
Probably not.
So that's kind of an extreme. Does it really mean that device is going to last that long? Maybe, maybe not. It probably just means that they took 10,000 devices and they had maybe one, maybe zero failures in the 100 hours of testing that they did at whatever temperature, and then they aggressively backtracked in the accelerated testing curve. So
that's to the point of ridiculous, really. Well, I wonder how accurate that will be. We may not ever know. It might be a few years short of that, but it reminds me of when LED lights, and I've said this on other episodes, when LED lighting first kind of came to the scene for consumers. Every light bulb was guaranteed for 20 or 30 or 40 years. And, they didn't even last 20 months before they all started failing. And so much for that, prediction technology, or at least the one they were using, right?
But this is probably what they did, the accelerated testing. And maybe they didn't look at their failure chain. Maybe they didn't look back far enough, because you've got an LED. Maybe they looked at the LED die. But what about the bonding wires? What about the solder joints? I had one of these LED lights that stopped working, like you said, after, whatever. And I unscrewed it, and I could hear things shaking around inside. So I opened it up, and parts just fell out.
Yeah.
At some point, it had gotten so hot that the solder melted and the parts just disassociated themselves from the board.
Right.
Right.
Well, there's all sorts of environmental things too, not to turn this whole topic into LEDs, but I was at a symposium not too long ago, and someone was speaking about the early production days of LEDs, and they used silver on a board, and it worked well until they started shipping these things to places like India that has a lot of sulfur in the air, and then they had just all sorts of like creep corrosion and all this stuff because of the sulfur, and the silver didn't like to play well in the same playground. And so there's all sorts of other than just 1,000 hours in a steam age tester or something, there are other environmental things too that probably change the paradigm and tweak the age predictor, the life predictor, and that is not just heat and humidity, but shock and vibration and climatic environment. Other than heat and humidity, there are all sorts of other nasty things that probably get into the equation or could get into the equation.
Yeah. Can I share a story with you?
Sure.
Am I allowed to swear?
Of course. We're an adult audience.
Okay, just checking. All right.
If any parent is coming home from soccer with kids in the car listening to this, first, shame on you, because your kids want more entertaining material than this. But second, children, close your ears. Okay, you're free to go.
Wonderful. And just parents, if you need to quick mute, the word I'm going to use, it starts with Jack, just so you know. All right. So this was back in, the early part of my career. I was helping design a lab, right? And we were going through everything. We did site visits to other labs. We looked at everything. Anyways, building's built, everything's going in, and we installed a acid cabinet, and we installed it next to fume hoods, right? We wanted it so people didn't have to track this stuff all over the lab and risk spilling or whatever. So it's this little half-height acid cabinet. Vent going to the outside, and this thing is stuffed full of hydrofluoric acid, which is a pretty nasty thing they use to develop silicone dyes. So everything's looking good. Come in one day, somebody has sawed off the vent from on top of this acid cabinet and installed this thing called an MDF. It's a little miniature server rack. So the IT department came in at the end of everything and decided that their box needed to go on top of this acid cabinet and with all of its delicate components. And they decided that this vent pipe apparently was just in their way, so they cut it off. So they had hydrofluoric acid venting into delicate computer electronics. This is why I wanted to call them jackasses, because there is no amount of engineering, the people who designed that server board, there's no amount of an engineering they could do to deal with they're called ID10T or picnic errors, if you've ever heard the term.
Mm-hmm.
So for your listeners out there, if you write down ID10T, so ID10T, it spells idiot.
And picnic was like people in between something in the keyboard or something, right?
Person in chair, a problem in chair, not in computer.
There you go.
It's just,
yeah.
There's nothing you can do. Nothing you can do to engineer against that use case. Right. Just engineers, I'm talking too much, but we'll give Greg a chance here in a second. But
you're good.
Okay. Hey.
I showed up to learn today. So.
Me too.
Engineers always try to make stuff idiot proof, while the universe is out there making better idiots every day. The universe is winning. I think that's the quote.
I love that. I've experienced that. Anyone who's been in business for any more than 10 seconds understands that. So Greg, let's wake you up now. And let's talk about the contract assembly business. I've wanted to get a CM on the show for a while. And so thanks for being my first. I think you're my first. You're not my first board fabricator, but from a CM standpoint. So I did a little research, and your company, Advanced Assembly's CEO, Lawrence Davis, is that correct?
Correct.
In a recent article stated that we expect components to continue to shrink in package size and that boards will be designed to a tighter density. And these trends increase the assembly difficulty. That's like a no duh statement, right? I mean, they're bad.
Sure.
Miniaturization is our friend in terms of convenience, and we can put things in our pocket and take it with us, but it's our enemy in terms of having to build it. So from both a PCB fabrication standpoint and an assembly standpoint, what are some of the specific challenges associated with miniaturization from your point of view as a CM?
Again, this can go pretty deep too. So, I mean, starting, obviously with the fab side and the procurement side with that, when you are using, whether it's a nanotechnology or, very, very tight tolerances, there's only a certain level that equipment today can go down to. And unfortunately, technology just in the world today is progressing faster than the equipment platforms that most CMs and board fab houses can keep up with. So when you're looking at, your general rules for minimum line and space and your board fab, you're looking for your general tolerances of, the board profile. When you're getting it mechanically routed, all of these different things, there's a certain tolerance that these things can hold. Cooper chloride and anhydrous ammonia can only etch to a certain line width before it just literally disappears. Smart CNCs and vision machines and everything like that can, route to a very, very minutia of a thousandth of a tolerance. But at the same time, sometimes you get board fab drawings and GD&T maps that are just not conducive to manufacturing. And that's, I guess the broad stroke of this whole thing is there's the engineering and design standpoint of what they perceive can be manufacturable, but there's also the realistic flip side of what can actually be achieved with today's current technology. And I'm speaking here as, in the masses, not the one-off company that might have a piece of equipment that can do something above and beyond anything ever seen before in real life. Because at the end of the day, most places just can't do that. On the assembly side, whereas 10 years ago it was unheard of to have an 0402 package size placed once, let alone 100 times on a board. Now that's commonplace. Now we're starting to see down to package sizes of 1005. And while the machine can have a tool to actually pick it up and place it, your X factor with assembly is always your paste.
Sure.
So whether, that is the X factor. It doesn't matter that the machine can place it, is can you reflow it, and is it going to have a proper solder joint? Is it reliable? Is it going to hold, or is it going to flink off if you look at it the wrong way? Those are all things that we have to take into consideration on the assembly side. And so
Yeah, I see these
you know
01005s getting placed and reflowed, and I just,
it's
for the
insane.
life of me, I don't understand how the solder paste stays separated. I don't understand why it's not just one big bridge, or small
Exactly.
bridge.
And
I,
and that's that today from an assembly level is the biggest challenge that we're faced with, is the being able to assembly to the level of technology that's being designed. And so while yes, we have a slight luxury on our end with advanced assembly, is that we actually use jet paste printers rather than stencils. Because on the stencil side, on the CM side of these things, if you have an aperture that's cut in 3 mil steel, and that aperture is either too big or too small, you immediately have to go back and recut, have a new stencil made, and it's just time, it's money,
sure,
that's wasted. And it's very, very difficult to dial in that aperture size if you are not well versed in using that. On our side with the paste printer, I don't know if you're familiar with them or not, but essentially it's a glorified dot matrix printer that just
sure,
deposits a round ball of paste at a determined aperture size and thickness that we program to it. So if there's a micro BGA package, or really tight QFN, or whatever things look like, it's we kind of have a little bit more control over that, from the repeatability standpoint. Prior to using that, this technology was coming in, and we were just going to get hosed on it if we didn't do something about it. So
well, especially in
it's a
your,
little react.
you guys specialize, advanced assembly specializes in low production runs, right? That's
Correct. Yeah. So,
your
yep.
sweet
Yep.
spot, the low production run. So
Absolutely. Absolutely. So I
stencils
mean,
don't make a lot of sense when you're building 5 boards. Or I even saw on your website you advertise you'll build 1 board if someone needs 1 board. That's kind of hard
absolutely.
to
Yeah. I mean,
justify a stencil for a production run of 1.
absolutely. Yeah. Lot quantity one is what we specialize in. Our sweet spot is 1 to 25, somewhere in there. But, that flexibility that we get, from the initial, design standpoint with engineers, and being able to get it to a prototype level, to a functioning assembly, there's a lot of moving parts to that. And so being able to get the pace dialed in and saying, hey, look, and being able to go back to them and say, look, um, frankly, your design sucks for what it's worth. Or, hey, look, we have a couple of opportunities here where you guys can improve this and open up this. Let's put some mask over here. You're getting bridging in this area. Those are all different areas that we love being able to support our customers on. It's funny too, because when Mark was talking, at the atomic level of where failure starts with boards, that's already after everything has been manufactured. I'm going to back up even further than that. And so I'll tell you, especially like a lot of like the MPI design engineers, and engineers who are new to the industry, they're very excited and very quick to get something to market. It's a competition. Everybody wants to have the newest product out there. And I think that, yes, their designs work, their schematics look good, all their files are in good shape and everything like that. But at the end of the day, they don't take into consideration the environment that it's going into, the reliability, how long does it need to function? If it's aerospace, if it's going to go and deploy in a payload, it's got to work for 25 years. I mean, technically, it needs to
Sure.
work forever.
You can't really go
We're
out and
not
fix it.
we're not pulling satellites out of the air to pull
Right.
them down and repair it. Um, SpaceX might pull some sorcery and actually develop that at some point, but
Yeah.
that doesn't
Now
happen
that they can
today.
actually land a rocket. Yeah.
Yeah, exactly. So maybe we're not too far from that. But I mean, these are a lot of things that I think people fail to take into consideration because they just want to get something released. And we will see designs come through here all day because that's the niche that we live in, of that new that MPI prototyping design, where the design isn't vetted out yet. It's not a mid volume. It's not a production. Not completely functional. And so, they'll design something and it'll go to vibration testing or atmospheric testing, burn-in testing, whatever testing is, on the docket for that assembly, and then it'll completely fail. And they wonder and go back and look at why, because they look at, yes, it's functional, but it does not have longevity built into that design.
Right. So let me go off slightly off topic here, although it's still relevant to contract assemblies. A few years ago, I was hired as an expert witness to help defend a contract manufacturer who was building a product based on the statement of work from their customer, and the statement of work was quite faulty, and then their customer was fueled by venture capitalist money, and of course, VCs want to see positive balance sheets, and they want to return. They want ship, and
Yep.
and there were some technical problems where some of the boards weren't passing tests, so they told their contract manufacturer, skip the testing, basically just ship. And the contract manufacturer warned them, and the customer said it's fine, just ship, and they did, and ended up with 50,000 units being recalled
Oh my gosh.
throughout North America. And then, of course, it all became the CM's fault because they did what they were told. And in fact, for my audience, there's I think we have a webinar coming up. It's a reprise webinar called SMT Wars, a story between a contract manufacturer and who did what their customer did and got sued for it. So look forward to that. But have you ever been put in the situation as a contract assembler where your customer is asking for something that A, is either technically impossible and you have to educate them, or that will come back to bite you in some way because they're asking for, skipping best practices or whatever? Do you ever have to determine the word no, which could make you more money than the word yes in some cases?
Yeah, absolutely. And so, one of the things that, that we do very well here is, we run into issues all day long where things are unmanufacturable. To going back to the CYA thing, for us, there's formal documentation that we need to have if there is an actual process change, just through an engineering change order from our customers, saying that if there is a process deviation, this is how this is going to be documented. And so for us, it's our leg to stand on, because at the end of the day, advanced assembly, we're built to print. There's nothing custom or any wand waving or sorcery that we do on our end to do above and beyond what the customer is asking to do. At the end of the day, advanced assembly places parts on boards, and we're really good at doing it. But at the end of the day, we are making sure that per spec and per print and per customer file requirements, per statement of work, that assembly is exactly what that customer ordered. And so if something is waived at any given point, there needs to be clear documentation and a process for that. So we know this is what you want and this is what we are doing. We are not at liberty to make calls that deviate from that process whatsoever. So there is certainly a risk for that, but I can't imagine that would hold up in court too well.
Yeah, this all settled after each side spent hundreds of thousands of dollars. But the irony is they did issue change orders, and then they said, well, you should have told us that the change orders were bad. I mean, basically, they were blaming them. They were armchair quarterbacking their own decisions and blaming the CM as, you were the expert. You should have told me I should not have done this. And
yeah, absolutely. I mean, at the end of the day, we are in a position to where if we're comfortable on a black and white level against a spec, that there is a that this is required, we can come back and say, hey guys, look, I mean, I understand that you guys want to waive this right here, but we're going to really recommend that you do this per this, and this. But, at the end of the day, if the customer is going to come back and tell us, hey, look, guys, I don't care about this, but I'm more concerned about this, then great. Give me documentation to support this, and we'll change our process.
Sure.
Yeah.
It's just one of the hazards of doing business, I suppose.
Absolutely.
Right?
I mean, there's always a risk in that, to where somebody's going to perceive that, something is, some shenanigans or some backdoor, things that are going on and everything like that. But, the thing is, on the advanced assembly side of it, there's a structure and foundation of a quality management system, of processes, best practices, procedures that are followed to the nines on what we do every day. If we didn't have that, I don't think we'd be anywhere near as successful and be able to ship what we do every day.
Sure.
So I appreciate, the foundation that we have of that, because at the end of the day, if we're stuck in a situation where we need to go back and review travelers or reflow profiles or bomb discrepancies, or things that would challenge what a customer got as a deliverable versus what we manufactured, we have evidence to support that until kingdom come.
Yeah, very
At
good.
the end of the day.
I also wanted to add, and Greg, you might know this number better than I do, but something like 95% of all of our orders go on hold for one reason or another, right?
Oh yeah,
Something
absolutely.
doesn't something doesn't make sense to us, and we will go
Yep.
back and get clarification from the customer before we start making that board.
Well,
Yeah,
that's good.
absolutely. I mean,
You don't just
there's a
see it and
point.
print it. You
Yeah.
don't just blindly follow directions.
No, this is, I mean, these things are critical to life, to whether they're, even if it's just a demo board for a trade show, or, something that is going to be rolled out into, something into a flight rev, it's got to be right. It doesn't matter what it's going into. The same level of attention and quality need to go into that build. So yeah, there is, typically on the turnkey side of things, if we're actually procuring the fabrication and the components and all the pieces that go along with that, there's a lot less hiccup for that. But on consigned kits is typically where we see the most issues, from overage issues, wrong parts. And there's so many customers that use internal part numbers in a cataloging inventory system that is personal to them, but have no industry relevance outside of their business. And so we're looking at a BOM, comparing it to what has been delivered to us, and they're pointing in both in opposite directions, and we can't tell what's what. So typically that's where things go on hold. Engineering technical questions are reached out to. Hey, what's this? Where is this supposed to go? Your files don't include this part. Are we placing it? That happens every day.
Yeah, very
And
good.
can I toot Greg's horn here for a second,
Of
Mike?
course.
Oh, come
Okay,
on,
you're
man.
gonna, yeah, you're gonna love this. So Greg,
Hold on,
Greg,
Mark. Hold on, Greg. You don't know what's coming.
yeah. So Greg, I mean, for the radio listeners out there, I want you to imagine a a young George Clooney,
Oh, come on.
or or a
Get outta here.
middle-aged Brad Pitt. This is Greg, right? Greg looks better than both those men.
I hate Greg a little bit more right now.
Greg
Thank
is
you.
responsible for our production. He's the one that makes the production lines go, and he makes them go fast. What do you think the fastest we can, you place an order with us. What do you think the fastest we can produce that for you is? I'm asking Mike, from time of order. What do you think the time
Assuming the
frame
board
is?
is already made.
Board's made.
I send you a board, or the board's already made. You pull it out of inventory.
Board shows up in our shop 8 o'clock Monday morning.
I would say a week,
Greg,
Couple
what's the
hours.
answer?
couple hours. So you all just sitting waiting for something to happen. A couple hours. Wow. At $9 million a board.
Exactly right. Exactly. No, it's the thing is, it's different about advanced assembly. Is, I mean, we honestly don't really consider ourselves to be a CM. We're more a partner, an assembly partner for our customers, our MPI and prototype customers. And so, there's a culture of quality and a culture of speed that everybody kind of lives and breathes here. And so if you go and walking through the front office, sales support, our engineering teams, all the pre-production areas, and then you go out to the production floor, there is it's a quiet chaos. It really is. And so it's a matter of everybody understands that every job is the hottest job. And I hate saying that, because we've all heard in manufacturing, if everything is hot, nothing is hot.
Right.
But it's just a sense of urgency. It's understanding that, hey, look, I understand that this order is critical. This 1-day turn, this same day turn, this 3-day turn is dire critical to life for the customer that's going to be receiving this in whatever, a day, 2 days, whatever. And it's my opportunity, it's my responsibility to making sure that we deliver on that.
Yeah, that's impressive.
Because, yeah, I mean, at the end of the day, quick turn, and I'm sure you guys would agree with this, quick turn is such a a diluted and overused word, especially in the EMS world. And everybody says they do it, but nobody actually really does it. They say they do it, but they're
They
like,
say they
we
do it, but
typically
like, don't ask. We hope we don't get it, right?
yeah, we pray to God that we don't get it. Yeah, we'll do it. And then they come back and they'll say, okay, well, what's a quick turn? In 5 days. Like 5 days? That's next year for me. That's nothing. And so for us, our splash that we want to make sure that we're doing, that we're holding up our end of the bargain on, is that we live in that 1 to 3 day world. And that's just normal life for us. And so we don't, we have 5 day lead times, we have 10-day lead times and everything, but it's, on the real core business that we are a quick turn assembler. The best part about that is you're getting quality built into that too, because at the end of the day, I mean, I've seen prototype boards that literally look like they're put together with frozen spit. It's insane. And parts are everywhere. Everything's misaligned.
Capped on tape, holding things down rather than solder.
Yeah, exactly. And I mean that with all due respect. I understand that people are trying to, get traction in this world, but we took on this part of the business, and we know it's a pain in the neck. I mean, it is not easy to do this, and the few companies out there who do that will attest to it. There's an immense amount of horsepower and clear vision on the staffing side, the equipment platform, a lot of capital investment to be able to get to that point to where that you can broadcast out to the world, to the electronics world, to our engineers, and say, look, we can do this, and we're not going to miss a beat doing it. So I'm proud of that. Our teams here do just a phenomenal job of being able to embrace that.
One of the reasons I reached out to you guys to see if you would be part of this interview, I wanted, as I said earlier, I wanted to talk to a contract manufacturer. I haven't talked to a contract manufacturer yet in our 36 or 37 episodes. And one of the things that attracted me to Advanced Assembly was your what seems to be a kind of a commitment to education. I didn't Google contract manufacturer, and you were in the A's, so that's not how I found you. I found you because I found your technical articles, and cool. I'm on your email list, so I get I get some buy from us, we're cool people, whatever, but most of the stuff I get is educational, and that's how my company presents itself to the world, through education, and I like that concept. So that's just FYI, that's what attracted me to
that's awesome.
Advanced Assembly.
That's super cool to hear that. Yeah,
well, it works. I mean, when you read something and you learn something, and then you think about, I need a contract assembler, I'm going to go to the people who taught me something, rather than the person with a slick ad and that says they're better than everyone else. I want to know what's
exactly
behind the curtain.
Yeah, I mean, at the end of the day, it doesn't really do a whole lot for us to just put out marketing blasts and just say, hey, look, we're here, we're great people, give us a try. We wanted to have this company to where people could actually, there's a gain out of it. Yes, you can get an assembly in X amount of days or X amount of hours or whatever that looks like. But at the same time, to use it as a resource, and on the educational piece, I'm glad you brought that up, because that's something that we actually do here internally, actually physically in the plant as well. We have University of Colorado. We have a lot of, kind of like, junior level engineers that come through here and do tours. We're, starting to do like small little workshops and everything like that, where we have people come through here and we're doing, a small technical presentation, talking about little pieces, about PCB, whether it's fab or assembly or everything in between. And really letting, kind of trying to be a resource, locally, for people that are kind of getting their feet wet too.
Sure.
We don't, there's not any walls that we like to hide behind. Actually, our entire company, like, the whole front of it's glass, you can see right in. But we invite people to to come here and to be able to learn, whether they're new customers or they come here and want to check the place out and never place business with us. It's our opportunity to educate them.
Sure. Educated customers make educated choices, I believe.
Absolutely. Absolutely.
So before we're starting to, the clock is running at like 2x speed, I think. So before we run out of time, I want to kind of go back to Mark for a second. Just when I thought it was safe to go back in the water, just when I thought all my fears, coronavirus and electrochemical migration, whatever, now I think you've taught me I need now to be concerned about cosmic rays. Was that your article, Mark?
That was one of my articles.
Yeah,
Yeah.
thank you very much.
That's got Mark written all over it.
It definitely does. Talk about it, like a physicist, talks about cosmic rays. So I have never heard of cosmic rays being a concern for electronic assemblies. So explain that to me again and to our audience, how we should now, in addition to all the other things to be concerned about, start worrying about cosmic rays for our circuit assemblies.
Well, in most cases, cosmic ray causing a failure, that's a 6 sigma event, right? That's a 1 in a million shot. So down near the surface of the Earth, the standard in New York is I think what they base things off of. There's probably about 13 cosmic rays per square centimeter per hour that will pass through your design, and that number goes up exponentially as you increase in elevation, right? The atmosphere is what's blocking these things, what's deflecting them, what's absorbing their energy. So when you start leaving the surface of the Earth, and you start moving into, I don't know, let's say Mount Everest type things, that number's in the hundreds or thousands. And by the time you get into space, low Earth orbits, the number is way up there. And if you get outside of the Earth's magnetic field or into these things, these Van Allen belts, I mean, you're just going to absolutely toast your design. There's nothing you can do to protect it other than get it out of that area. I mean, yeah, there's a little bit of shielding, but it's really not going to help you. So one of the statistical ways that you can look at failure analysis is by looking in failures in time. It's basically how many things are going to break per billion hours of use. Measurement unit is a FIT, F-I-T. So you look at something, and let's say it's 14 failures in time. You're going to get 14 failures per billion hours of use is what you should expect. Well, if you've got one board and you've got a FIT of 14 overall, you probably don't really have a problem, right? You could get hit. It's like winning the lottery, and it could destroy your board, but by and large, it probably won't from a statistical standpoint. Have you ever heard the golf ball and the blade of grass analogy in statistics?
No, I haven't. Tell me.
Okay, so basically, this golfer's out on the field, hits a golf ball, goes flying out into the field, and it lands, and it just smashes this blade of grass, and the blade of grass asks, "Why me, Lord? Why me?" And from the blade of grass's point of view, of course, that makes sense. I mean, right? Why him? Of all of these things, why did it hit that one blade of grass?
1,000,000 to 1.
But you look back and you realize, well, hey, it was going to hit somewhere. It was going to hit a blade of grass. So you start increasing the number of golf balls that hit off in all different directions. And when you're increasing the number of golf balls, you're starting to increase the number of products that you have in the field, right? You hit 10, it's going to hit more. You do 1,000, you do 10,000, you do 100,000 products, which some companies make. Well, now you've covered the field in golf balls. You are going to have a failure due to cosmic rays at some point within the next 2 years. Something bad's going to happen. So is it going to be a mission critical event? Is it going to be the reason that somebody dies? I don't know. But cosmic rays have been attributed to failures in airplanes, causing these things to plunge hundreds or thousands of feet. They've been attributed potentially to changes in vote counts during a voting election.
Don't let our current president hear that. I'm not going to go there, but that's going to be
Mark,
the next
have you data to support that?
Yeah, exactly.
So
fake news, boys, fake news.
These fake cosmic rays.
There you go.
Presumably came in and they hit a little bit of memory. So the reason that they think it was a cosmic ray upset was because the vote count increased by exactly 4,096, which is a power of 2. So if you get a bit flip in a memory register, that would explain it. So what causes the bit flip? Well, radiation or a cosmic ray. So when do you need to start worrying about it? If you've got a mission critical thing, if you've got lots of products in the field, you certainly need to start considering it. Self-driving cars. So let's say you've got 100,000 or 1,000,000 products in the field, and I don't know exactly what those are, but let's say they're the accelerator control of a hybrid vehicle made by a company that rhymes with Schmoyota. Okay. So let's say you've got these things in the field, and these things can be affected by cosmic rays. And let's say if a particular bit flips, the car will accelerate uncontrollably, and people will crash. The cars will crash, and people will die. Right? Has that ever happened? Well,
With Schmoyota, it has, yes.
With Schmoyota, this fictional company, it absolutely has. So what do you do about that? So you can start looking at these failure trees. You start backtracking. You go through every part and you ask yourself, what happens if this part fails in the worst way at the worst possible time? What happens if this bit flips? Is that going to, like I said, cause an acceleration? And if it is, what are you going to do about it? So NASA for years, and one of the things that got us into space was this idea of triple modular redundancy. You have 3 of everything. If you've got a sensor, and let's just go with the simple temperature sensor for now, right? And say it's a critical system, so you need 3 of them. Well, if all 3 measurements agree, great. We know it's a good measurement. We go with it. If only 2 measurements agree, we're still good. We just assume the 3rd one is, something's happened to that. Maybe we power cycle, see if the sensor recovers. But as long as we have 2, we still know that we have a good system and we can trust it, right? We might throw up an error flag and say, hey, we need to go in for servicing, get that 3rd one fixed, but we still have a functional system. It isn't until 2 of those sensors fail that you have a problem, because then you don't know what you can trust. Does that make sense?
Yeah, absolutely. I bet Boeing wishes they had that philosophy on the Max 737 Max issue, because they listened. Yeah. They allowed one sensor to fail and believed the other one was right. So anyway, that's a bit of a tangent.
That is exactly the point. Right? You ask yourself, what happens if this thing fails in the worst possible way? And this company, Boeing, by the way, to disguise things, all I really do is add a little bit of Yiddish in there.
Add a little SH in front of everything. Yes. I've broken the code.
So Boeing, right, they never ask themselves, what happens if this thing fails at the worst possible time? Because what happens is,
takeoff, yes.
This MCAS system kicks in, and a mechanical adjustment of the rudder points it down to the extent
the elevator.
I'm sorry, you're right, the elevator, so that the pilots can no longer positively control the pitch of this plane.
Yep.
That is a huge, huge mistake, and many people died because of it.
Sure, and the planes are still on the ground as of this date, and trying to get FAA to certify them again. Yeah, huge loss in reputation and financial cost for not just Boeing, but the entire airline industry that has those planes on order.
It should be a huge cost.
Absolutely.
And a huge loss in reputation. It's a huge and completely avoidable mistake.
Absolutely. So when I was a kid, you talk about redundancies. This is just kind of anecdote here. I used to get into all sorts. I was always kind of clever. I wanted to understand how things worked, so I found my parents' appliances good subjects to teach me. So I would take all my parents' appliances apart, clock radios and whatever, and take them apart.
Were these functioning at the time?
Oh, yes. Well, they were at
perfect.
the time. They were, and they were largely functioning when I gave them back. There was a few pieces missing, but I wanted to see how things worked. I just wasn't all that interested in figuring out how they go back together. That was where I got into trouble. But I used to, like a transistor radio is a good example. I'd have this transistor radio, and I would look at the circuit board, all through hole, single-sided, soldered on the back, nothing on the front. And I would take a little pair of snippers and I would snip off leads. I'd, basically disconnect certain components. The radio would still play.
As one does, right. Yeah.
I'd disconnect another component. The radio still played. I could disconnect 3 or 4 components before the radio went silent. And I remember thinking as a kid, not understanding anything to do with engineering, the folks at Sony, whoever made the radio, they're crazy. They're putting parts in they don't need. And I thought about, I should write a letter to Sony and say, whatever this thing is, you don't need it. It works without it. And then, later, of course, I realized that those are there either as redundant things or to fine tune or to increase the antennas, sensitive, whatever they were for. It would still work without a few of them, probably not in every environment and probably not as well. But from my standpoint, my layman young, naive mind standpoint, I just thought it was a complete waste of components. And and I would keep going until it broke. And then I would solder it back on. But I'd leave the other ones out. So everything I gave back to my parents was always a little bit lighter than how I got them.
Well, that's how taking things apart goes. I mean, you want extra parts left over at the end.
Sure.
But
exactly.
I suspect you're asking, or you're bringing up that anecdote to ask a question related
about
to reliability?
That was kind of a precursor to my question, which you already kind of went there, your fault tree diagrams. And, how many things have to fail before another variety of failure gets brought into the equation. And you talked in that particular article about redundancies and things like that. That's what spurred that memory.
Yeah. Well, not all part failures are catastrophic, as you mentioned, very clearly. So sometimes what those parts do is they control, EMI emissions. Sometimes what they do is affect, how will your radio still work if you're 50 miles further away, or if you remove some sensitivity. You just don't know. So not every part is critical to design. I really doubt they designed redundancy into it, but there is something that I think is important for engineers to consider related to that, in taking parts out. When you design something, the passive components, your capacitors, your inductors, resistors even, they don't have the same characteristics on day one that they do on day 1000. Right? These things derate themselves over time. And you might have it working on day one, but you leave that capacitor out, and maybe now it dies 1 year from now instead of 5 years from now.
Sure.
So you don't always want to design things for how they're going to work on your test bench. You want to design how they're going to work
in the real
and
world.
Incorporate that derating that occurs. You just never know. I'll give you another example. At a university that participates in the Mars Rover Challenge, it's this little competition. They go out to Utah. They built these robots that have to go and do tasks. And the university sounds like Cal State Schmullerton in Fullerton, California.
Yes, that's where my daughter went to school, Cal State Schmullerton. Yes.
Schmullerton. So anyways, I went there too, actually. It's a great school.
Yes.
So these guys had designed their robot, and they had to create some sort of an emergency off circuit just in case, something happens and they have to shut this thing off in a hurry. Now, most people would have used fuses or switches, but the young engineer that was in charge of this, he's a junior, he decided to use 3 in-channel MOSFETs. The idea being that if something happens, and by the way, they're running like 80 amps through these 3 MOSFETs that are set up in parallel. There's all sorts of issues with this. But you have to ask yourself, what's going to happen if this MOSFET, because they fail. As time goes by, they're not going to work like they do on day one. So what happens if, one of these MOSFETs fails? Well, the failure mode is going to be that this thing welds itself open. It's going to become a short circuit. It's going to pass a ton of current. You will not be able to shut this rover off. And then when that one shorts out, it's probably going to cascade the failure to the other 2 as well. So, yeah, it worked. I mean, you can't argue with it. It worked on day 1. But is it going to work when you really need it to? That's why sometimes it's best not to live on the bleeding edge. If you're going to put something up in space, the Voyager spacecrafts, we launched in the 70s. Voyager 2 is still sending data back today, right?
Yeah, I remember that one. When I was a teenager, I submitted a drawing to NASA at a contest to see if we could put your drawing on as the logo of that particular spacecraft, and I did not get chosen for that. But I do remember. That's why I remember so well that particular mission. It's amazing to think that many years later, in the harshest of harsh environments, that everything's still working. But of course, back then the electronics were all through hole, and the conductors were miles apart compared to what we have today. I doubt a modern high density circuit assembly with low standoff components and bottom terminated components that trap everything would work so well so many years later in that environment.
We don't know, but I guess my point with that story is, I mean, use best engineering practices when you can.
Yes.
Don't live on the bleeding edge just to play what if, because, eventually it will bite you.
Yes, absolutely. I think that's a good point. And that is a good point to kind of wrap this up. Mark and Greg, thank you so much for being my guests today on Reliability
Thanks
Matters.
so much for having us. It's been great.
You have not disappointed at all. I think I'm so glad I reached out to you guys. And I got a lot more than I expected to get. Not just assembly related best practice stuff, but now I'm afraid of cosmic rays, and I've got some good golf ball analogies now that I didn't have before.
Well, hey, if you ever want to come out to Santa Fe Springs and check out our Rigid Flex shop, we'd love to have you. I'd be happy to show you around.
I would love. I in this business, my dad had a saying many years ago: "You learn your whole life and you still die stupid." So I'm on this learning curve, particularly with this podcast. I get to talk to folks like yourself that know a whole lot more about particular subject matters than I do. So I enjoy the learning that I get and the experience that I get from talking to folks like yourself and others that teach me some things, and hopefully our audience finds that same takeaway. So yes, I'll take you up on that. I'll reach out to you offline and
Sure.
Get a tour. That sounds great.
And one quick disclaimer for
Sure.
your audience.
Yep.
I have no idea what I'm talking about. I made up all of those words as we went along. So
So tell your lawyers don't bother.
Tell your lawyers, if you've got nothing better to do than design something because some guy you heard on a podcast told you to, my name is
Mark Schmooze.
Schmooze.
Mark Schmooze. I had a feeling we were going to go there. Well, one day we'll be able to schmooze around your shop, and I'll see all the things that you don't know about.
Yeah.
Well,
So that's like, don't try this at home. Whenever you see one of those commercials, don't try this at home.
Mike, if you're ever in the Denver area and want to stop by Advanced Assembly, we'd be more than happy to have you through here.
I'd love it. Yeah, I'll definitely reach out.
Open door is always there.
I appreciate it. And gentlemen, thank you so much for your considerable time, and thanks for sharing your considerable knowledge with us. Myself and my audience greatly appreciate it.
Great. Thanks again for having us.
It was fun. Thanks.
Well, that's another episode. Thanks for listening to the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on iTunes, Spotify, iHeartRadio, or wherever you get your podcast. Reliability Matters and other reliability-based podcasts are available at Circuit Assembly's PCB Chat at pcbchat.com and at Ascendo Reliability at reliability.fm. Thanks for your comments. Please keep them coming. Send comments and episode suggestions to Mike at mikeconrad.com. That's Conrad with a K. Until next time, thanks for listening and keep doing it right.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.